Great. Well, thank you so much. I'm excited to be part of this kind of flashback image. So I'm sitting in front of this image of a beautiful network or phage of M13 bacteriophage. And the image that we originally submitted in I think it was the first KI Image Awards was viruses that had been genetically altered, M13 bacteriophage that had been genetically altered to grow battery electrodes. And this image was taken by a former graduate student of mine, Colonel John Burpo, who's now a professor at West Point. And so what this image showed was that we could take these M13 bacteriophage, which are beautiful, long, thin viruses shown right here that have a DNA sequence that codes for the proteins that make them up. We could genetically program them to grow a whole bunch of materials that we're interested in. In that case, it was for battery electrodes. Over the last 10 years since this time, I have not lost my love for the structure of M13 bacteriophage. This is a picture here of M13 bacteriophage showing the kinds of things that you can build out of it. And this is my great collaborator, Paula Hammond, and she and I worked together to build phage-based solar cells and batteries. We also showed that you could use these same structures that were in the image from 2011 to build catalysts, drop-in fuel replacements, building supplies, and we moved deeper into understanding ovarian cancer using these same bacteriophages, as well as artificial photosynthesis as well. This is a movie of where we went in batteries. This is a virus that has been engineered on its beautiful little protein coats to be able to nucleate in solution out of water, manganese oxide solution with a small amount of palladium. What we showed is that the virus template made these really great nanostructures that were high surface area and very reactive as a catalyst electrode in a lithium oxygen battery application. And we showed that through this genetic engineering over time, that we could get record-breaking lithium oxygen battery electrodes. And we thought that one day these could be used for electric vehicles to increase the time between charging. And so here it is functioning in a device with the idea that it could be eventually used in transportation. Since then, we have also used these same kinds of structures to absorb small gas molecules, including CO2, and we've used them to take CO2 and convert them into other more useful products, including energy storage for batteries or smaller molecules. But we're in the Koch Institute, we're in the KI, and we wanted to use them for applications in cancer. And the particular kind of cancer we wanted to start with was ovarian cancer. And the reason we wanted to look at ovarian cancer was because if you catch ovarian cancer very early, you have a good 5-year survival rate, but most of the time it's not caught early. And at distance, you have a 29% survival rate. So we thought, what can we do with our expertise in phage and nano to work in this area? So what we did, and this is in collaboration with Sangeeta, in collaboration with Paula Hammond on certain ovarian projects. And what we did was we engineered these viruses to find tumors and to carry with them a structure called a carbon nanotube that's fluorescent in wavelengths that are in what's called second window near IR, so imaging above 1,000 nanometers. This was really important because it allowed us to image inside of the mouse or inside other organisms without having to open them up, and so looking deeply. And so this image shows basically pre-injection. This is a mouse that has a high burden of ovarian tumors. This is what it looks like pre-surgery, where you can see a high density of tumors. A surgeon goes in and doesn't look at our map of where we think that the tumors are and just does surgery and leaves a lot of tumors behind. And then if we give him the map, he was able to go in and remove more tumors. So we're using these viruses now as vehicles imaging agents. And what we found is that we could find tumors that are much, much smaller, tumors that are on the millimeter length scale with these types of virus-based delivery systems. We went on to build a real-time surgical guided imaging system with Lincoln Labs, MIT Lincoln Labs, and Mass General, where we could help surgeons find the tumors pre-surgery and then help them during surgery to remove very small tumors. These are tumors that are millimeter-sized tumors. And by doing that, we were able to have a 40% increase in survival rate of the mice in this example. We're now working on sending these materials for testing at NIH, and we're working on a human scale instrument for image-guided ovarian cancer surgery. And this is showing that we can find very small tumors that are even less than a millimeter in size. Something that's new, that's also pretty cool, that's based on the same structure, is that we're able to make really high surface area carbon viruses that can neutralize chemical warfare agents like sarin and soman, and they can neutralize toxic industrial chemicals. And so we worked with the Army to build masks out of these that could be used by first responders in difficult situations to neutralize chemicals that they would come in contact, including very, very deadly chemicals. And this graph here shows what our material does. Gives a long time before you actually, the chemicals break through. We said, well, wow, if you can do that, maybe we could make masks for smog and pollution and wildfires based on the same kinds of structure, which we did. And right before the pandemic, we started working on making masks that could prevent viruses from filtering in. And so we repurposed the same structures we use for batteries and for chemical warfare agents, and we used them to make masks that could not only prevent very small viruses that are smaller than the SARS-CoV-2 from entering, but could also neutralize them. So this data here shows that these two formulations of viruses we engineered to grow carbon-based structures neutralizes viruses that were normally 1 × 10⁻11 to 10 viruses that are still able to replicate. So right now we're very interested in transitioning this for future kinds of viruses, bacteria viruses that could be helpful for doctors, first responders. And so with that, that tells you kind of the evolution of where we're going. We think the M13 virus is an amazing material that can be genetically engineered and altered for many different kinds of applications. And the image that we showed 10 years ago is being tested in drone wings to increase the flight time, battery flight time in drones, to all kinds of other batteries. And that technology has gone on to look at cancer and gone on to look at also ways of preventing the spread of viruses and a way of neutralizing chemical warfare agents, which could be used for first responders, or eventually one day used for people that are in situations where in other countries where they may come in contact with very toxic chemicals. With that, I'd like to thank you for including our flashback material, and thank you.